So the problem that we had yesterday, and I didn't write down which mass was which, by the way, so you'll have to help me on this. These were
They were the same mass M.
M, okay. But were they the same?
Well, it was like
Yeah.
that way, and then they combined to make it.
Yes, okay. And then, so I had this one go down
10 meters per second.
30 degrees.
10 meters.
10 meters per second. And then this one is going down at 8 meters per second. That's 45 degrees. And then they combine in some sort of awful conglomeration. And then this thing moves probably with some speed. Maybe like that or something. I don't know. What do you find? Okay, and the question was, we wanted to figure out what V final is, right? So that means we want X and Y components of that. What was the answer that I gave you?
You give us
5.33 Vy is equal to negative 5.33 meters per second. So I have that, and Vx was
1.5.
1.5 meters per second. What's that?
I got both positives for some reason.
I think this one
That
will,
one's
this one will be positive, I guess.
It should be.
Yeah, X and Y. Okay. All right, let's see how we
It
can
would have
get
been
these
negative if
answers,
they were,
okay?
the velocities were switched.
And so when I first told you the answers last time, I was actually wrong because I accidentally divided by 3 mass instead of 2 mass. So these are the real answers, okay? Let's go ahead and see if we can do these. So this is just to conservate, this is what type of collision?
Inelastic.
Inelastic, completely inelastic. They stick together. They're traveling with the same velocity at the end. And but we know momentum is conserved in every collision. So we're going to start with conservation of momentum. So first of all, let's see if we can figure out the total initial momentum with these and these masses together. So Pi initial is, let's call this mass 1. And this mass 2, it would be the sum of the momentum of mass 1 and mass 2, which is m v1 vector plus m v2 vector. Now, I think in this one it'll probably be easier to just do x and y components separately. What do you think? So that's what we'll do. We can do, so P initial x is P1x plus P2x. This will be the x component of the momentum equation. And so that means that m, or 2m Vx, which is the final x component, that's both, well, that's, I guess I'm confusing you right here. Okay, we'll just do P initial x is equal to P1x plus P2x. It'd be m V1x plus m V2x. Okay? So V1x, we got to figure out the x component of this velocity here. So how do we do that? So that means you want to figure out if this is your length, your magnitude of velocity, you want to figure out how far it goes over in that direction. So this length here. So if this is a 30-degree angle, and this is magnitude 10 meters per second, what's this? Yep, so V1x is 10 meters per second times cosine of 30 degrees. And that's square root of 3 over 2 times 10 meters per second. Okay, how about V2x? So we want to, so if this goes down this way, that amount, we want to figure out how much it goes over horizontally, like that. So it goes down, the magnitude's 8 meters per second. It'll go over this length, but in the negative x direction. So what is this length here? So it'd be negative 8 meters per second times cosine of 45 degrees. You guys follow that? And so that's minus 8 meters per second over square root of 2. Because cosine of 45 is, well, anyway, you can plug those into your calculator if you don't know those. Okay, and so I can plug this in here. So this is going to be m square root of 3 over 2 times 10 meters per second minus 1 over square root of 2 times 8 meters per second. And this is the initial momentum in the x direction. Momentum's the same before and after the collision. So that also has to be the final momentum in the x direction, right? And that would be 2m vx. The initial momentum in the x direction has to equal final momentum in the x direction. And that's what this is. So I can divide through by an m, divide through by a 2, and that's going to be my my final velocity in the x direction. So when I plug in numbers, I should get this. Okay? Does that make sense to you guys? Now we do the same thing in the y direction. So this vector equation, you know, here is really two equations if I have x and y. So movement, so I can start out and just write it as p initial y, p1y plus p2y. You could write it like that. That's the second, that's the x component of that equation. This is equal to, so I have m, that's equal to m v1y plus m v2y. The v1y and v2y, what would v1y be? So I want to figure out what this length is, right? So what would it be? What's it? So it'd be 10.
Meters per second.
Okay.
Sine of 30.
Yeah. So if this is the hypotenuse, 10 meters per second. I'm looking at this side, so that's the opposite side. So the opposite side is the hypotenuse sine of the angle. So sine of 30 degrees. And is it positive or negative?
Negative.
So I got to put a negative sign on that by hand. V2y, what would that be?
Negative 8 meters per second.
Negative 8 meters per second, cosine of sine,
Yep.
sine of 45 degrees. All right, and that's minus 10 meters per second times 1/2, and this is negative 8 meters per second times 1 over root 2 again. And I take those, I plug it into here. And I know that this initial momentum in the y direction is going to be the final momentum in the y direction. So I could say m times negative 10 meters per second over 2, negative 8 meters per second over the square root of 2. I factored out the m from both of these out front. equal to 2m dy. Divide through by the m's. Divide through by a 2. And when I evaluate Vy, I should get that. Okay? You guys get that? So what we did is we were just careful about splitting up these momentums into x and y components or vectors. And so we have to add vectors. And so you have to add it in the x direction, you have to add it in the y direction. Okay, let's go ahead and do some problem reviews. So I'm going to go ahead and set this thing up. Let's see what happens. Did that light turn off automatically when I started? That's pretty sweet. Yes. Okay, so which group wants to come up first and present their problem?
Go.
Travis, you got a group? There you go.
Yeah, yeah.
All right, you guys go first, okay?
Why? He said they want to go.
Let's get it over. Let's get it
Okay,
over.
well, we need to go, I guess.
And you'll be happy.
I don't know. We were gonna make our problem sweet,
Okay, so I'll go ahead
I really don't know. If you guys
and let me zoom in here a little
any
bit.
error, I go. And then we have to write on. I didn't know it's so simple.
Okay.
I think we have a problem.
Okay, so go ahead and put your problem in.
Okay. Sure. Okay.
So can you guys read this? So what's the problem?
Okay, we have a problem here. It says that imagine you have a beam that's held up by a cable. So this is the beam, this is the cable, and we are wanting you to calculate the force, the tension force in the cable here. And we also have a hanging mass of 30 kilograms here. And so in order to do this, you have, we know that in statics that the sum of the forces are equal to 0 and the sum of the torques equal to 0. So we calculated all the torques. So the torque in the beam is half of, half of this distance here, 3 meters times the mass and times mg. And it's negative because it wants to rotate in clockwise direction. And then some of the torques in the hanging mass, also this distance times the mg. And it is also negative as it wants to rotate clockwise. And then finally the torques in this tension over here. And so it will be the distance. We chose to do the distance times force t perpendicular. And so the distance is 6 meters. And we found t perpendicular by using this angle here, 60 degrees. T sine of 60 degrees will give us that perpendicular distance. And it will be positive as the cable wants to rotate counterclockwise. And then we summed up all of these torques, set them equal to 0, and then since we're wanting to solve for this force, tension force, we took it by itself to the other side, and then we divided by 6 meters sine of 60, and found the tension force to be 352.2 newtons.
That seems pretty well done. You were ready. So that's a pretty good standard standard problem, so. I'll
Yeah,
take that.
can we write our name? I didn't finish writing our name.
I'm not, yeah, I don't mind if
Oh, you don't
my
mind?
name or not, I'm just.
Okay, yeah, you can have it.
Okay, who would like to go next? How about you guys? Let's work our way. Does that make sense to everyone? All right. Another Superman type one this week. You guys Superman, are you a Superman fan?
Everybody's a Superman.
Nah, he's too good. You're annoying.
Good morning, class. No problem. Lois Lane was pushed out of a plane by Lex Luthor at a height of 5,000 meters. She weighs 54 kilograms. Superman catches her 139 meters off the ground when she's falling at a velocity of 53 meters per second. What is the work done by gravity, and what is the total work? So, what we did was we took the total work and we put it into this equation. See that?
Okay.
And pretty much just plugging numbers in.
And it's off the ground, so you have to take that 5
Yeah,
and subtract the height,
Yeah,
okay?
and find the distance.
Why is it cosine of 0?
Because it's in the same direction.
Yeah. Good.
To find the work total, we had to go through the kinetic energy. And since we had the final velocity, just worked it through.
Okay, that looks pretty good. See what they did? Total work was changed in kinetic energy. Work done by a force is the FD cosine of the angle between the distance and the force. And they looked at both of those. Good. And I won't worry about that bonus one. You might want to cross it out. That looks pretty tough.
What is it?
It was a lot of more numbers that we'd have to give.
All right, very good. So that was a work and energy one.
Yeah, I like your best.
All right, how about yours?
It's just.
Let me make sure this thing's still recording. My resolution, it doesn't go for very long. Okay, I think it's good. This might be surprisingly hard to read on there.
Oh, yeah.
Should let us take pictures of the papers.
Yeah.
Yes, well, yeah, I guess we could do that.
Just spread them out at the end of the class.
Okay, so we have a problem where a toy car, we didn't say it, but it starts at rest on a ramp. That's 15 meters long and is inclined at a 35-degree angle. It weighs 25 kilograms. 20 kilograms, and is pushed up the ramp by a force that is exerted in the horizontal direction and has a magnitude of 100 newtons. So we want to find the work done by the force and then the speed of the car. So,
This probably feels strangely familiar.
Yeah, it is. We kind of just changed the numbers a little bit and asked another question as well. But so we found the work done by the force times the distance times the cosine of the angle of the ramp, and then when we found that work, we were like, okay, that was maybe a little too simple. Let's add something else in there. And since the toy car started at rest, when you go to find like the total work, it would just be this number here. So we plugged that into
You'd have the work done by gravity too.
well, yeah. And then we plugged the work into the kinetic energy equals 1/2 mass times the velocity squared to determine what speed the car was being pushed up the ramp.
I think for the total work, you also need to have the force do the gravity in order to get the final speed.
But isn't that just, like the kinetic, or like the work final minus the work initial?
Well, so you'll have, so it raised, not only did that horizontal force do work like you have it, but gravity did negative work because it went uphill. So you want to also have to include that. And that'd be the same as taking the negative of the change in potential energy.
Okay.
So just do MGH, that would be the work done by gravity.
So anytime gravity does work going up, it's negative, and then going down, it's positive?
Yep.
Okay.
Oh, okay.
So, okay? So you'd have, yeah, so you'd have to include that.
Okay, do you want us to change it and then bring it back to you?
Put it there, it's
Okay.
fine. Next, let's see, how about Ricky's group? All right. Lots of energy ones.
So we have a drag car that runs a quarter mile, and when it crosses the finish line has a speed of 350 miles per hour. So what is the horsepower? So we found the work total based on the change in kinetic energy. And then we found the time that it would take for the car to do the quarter mile. And then we converted the work or the work over the time to power, and then found horsepower by dividing by 745.7.
And that'd be the horsepower at the wheels, right?
Yeah.
Cool. Without including the fact that they spin a ton.
Yeah. Yeah.
At the beginning.
Right.
That's a lot.
So so they found the work total, and then what did they do?
They found the they wanted power, which is work per time, right?
Yeah.
So we had to find time.
Oh, so you use the kinematics
Yeah.
to find the time, okay.
Because we couldn't remember what the other formula was.
Okay. And you assume a constant acceleration, which is fine.
Yeah.
And that makes sense to everyone.
Yeah.
Okay.
Would we need the, what's it called?
The conversion.
Yeah, the
between
conversion,
horsepower
yeah.
and watts. Yep, they have it up there, and if that was on the test, I'd put that up there. Yep. If I can't remember the conversion. I vaguely remember 700, roughly 700, but it looks like 750.
Yeah.
Would be better, yeah. Watts to 1 horsepower.
Wait, what
50, 746.
So right in the question, it says 1 HP is equal to 745 watts. Good. Yeah, those top fuel drag cars, by the way, if you guys figure out and can explain to me how that the tires of these have to be really flexible. They're very thin tires. They're more like balloons than normal tires. And for some reason that makes them able to accelerate at 5G, even though the coefficient of friction doesn't seem to be 5, but I don't understand it myself, but I haven't really worked through and thought about it too much, but it seems pretty interesting. So, yeah. Well, thank you. Yep. All right, Samantha?
I don't have my trigger.
Okay.
Okay. Mine was just finding what the final velocity would be of 2 droplets of water if they're traveling along the same plane, and if the collision was completely inelastic. And so you just,
Okay.
it's pretty simple.
Good. All right. Everyone follow that. So one ball hit, one droplet hits another droplet, and they get glom together. So, thanks. Brittany?
Okay, so my question is, from what height would a car have to fall to gain the kinetic energy equivalent to what it would have when going 90 kilometers an hour? So we changed kilometers per hour to meters per second, and then it's like the kinetic energy initial plus the potential energy initial equals the final ones, but it ends up just being 1/2 mv squared equals mgh.
Everyone follow that? Good.
Does that make sense?
Yep.
Okay.
So it only took about a little over 100 feet, huh? Okay, let's see, you guys came one up already, right? Jessica.
Okay, so this physics student decided he couldn't take the next physics exam, so he wanted to jump off this building.
Are you trying to say something?
Yeah. The initial velocity is 150 meters per second. It's 650 meters up in the air. So what's the final velocity? Yeah. And then, so we use this kinetic and potential energy equation, you know, and then cross off the masses.
Burj
And,
Khalifa.
hmm?
You know that giant building in Abu Dhabi?
He really wanted to die, I guess. Yeah, and we just plugged in the numbers and. Yeah.
Okay. Cool. Well, don't do that, guys. Feel bad.
It's not.
It's not worth it. All right. You guys ready? Spencer,
No, I don't have to.
you got a problem? Sure. Well, I'll let these guys get. I'll let Mason go next.
Oh,
I knew.
ours was just a little simple inelastic collision. Two cars collided with each other. First one going 50 meters per second. Second going 60 meters per second. And their weights combined divided by the total add-up. 5.7.
Okay, and then you divide by, okay.
So simple inelastic.
Going, so are they coming towards each other or away from each other?
They're going
Into each other.
Yeah.
Oh, okay, I got you.
crashes into a big,
Yeah.
Okay.
so there's a car out.